So I'm standing in for Toby. The younger organizers convinced me to give a small talk where I tried to say a little bit about what was Smith's theory, mainly like classical, but also with a view towards sort of modern kind of Smith's theory. So that, yeah. So you can ask questions also if you have questions as we go along. That's allowed. So we had Smith's theory come up in the first talk. So this is P.A. Smith's theory, and there are some discussion what does that word really mean? And for me, I guess it means what's the relation between x and the fixed points. So, and here it's important that x is a finite p-space or PCW complex or something like that, and we'll can talk about later how we want to relax that, because of course we might not really want something which is finite. We want some sort of homological finiteness conditions, and then all of this will be P will be a finite P group. And most of these theorems, by some sort of induction, we can reduce to the case where P is just Z modulo P, but of course not always. So that's sort of what we basically want to study, is to study this sort of relation. So we picture, we have, and sometimes we call P for B, so Z modulo P, and then if we want to build X, then we build sort of X from the fixed points by attaching free cells times V modulo E. So we attach a bunch of cells, and then we get the whole space, and then you can ask yourself the question: what happens with this attachment procedure here? Okay, so the first thing to note is that, first of all, this is a P group condition, and it's something about like everything is with mod P cohomology or congruent with mod P or something like that. So that's why we're sort of only dealing with P groups. And the other thing which is up with that is this finiteness assumption. And how does that play in? Well, as was also mentioned during the first talk, but just to repeat, so without, no, maybe not the first talk, during Leonard's talk, right, he mentioned Elmendorf's theorem, which says that without the finiteness assumption, it's just functors on the orbit category, the opposite orbit category. Then we have, like say, Z modulo P spaces will be given by functors from this category here to spaces. So then, of course, you know, if we want to see we just not know what the whole space is, then we can see we have basically no information here. The fixed points would be the value here, so we should just have to have some we can put anything here which just maps to whatever is fixed under ZP at this point here. So that means that if we give ourselves the data of a homotopy type which we want for X with some action, then whatever the fixed point is can be basically anything. So that says that Smith's theory is only something with some sort of finiteness condition. So we're not arguing about whether there should be a finiteness condition, but just sort of what exactly this finite condition should be. The other thing is then now I say everything with actual fixed points, but sooner or later, we might want to replace the actual fixed points by some sort of homotopy fixed points. the actual fixed points by the homotopy fixed points. Okay, the third thing, which is good to observe, which is that, well, if you're working in a stable setting, then you could say, well, should you also replace x by the homotopy fixed points in that setting? And there the point is it's a little more complicated, and you can see that already when dealing with sets. So if we take which f is a set, and then we sort of want to consider the stable version, so that would sort of be trying to just linearize the set and take fp on the set here. Then we could try to take the fixed points under, say, set modulo p of this, and that would of course have inside here fp of the actual fixed points, but we would also have orbits of things, right? So we would likewise have the thing which was generated by orbits applied to some element x in or v in the where v is in. So we have like these things which are not really fixed points, but are just sort of just because we can sum up in the group here. So this says that if we're wanting to do things in a stable setting, what we should really do instead, we should never sort of do, if we want to study sort of what corresponds to the geometry, then we should not study the fixed point, but we should study some sort of Tate fixed points where we mod out by all these transfer maps here. So if we took just the fixed points here, modulo these transfers, so these sums over then we get the right thing. So these are some warm-up considerations that you might want to see here, and here of course we see. So here I'm taking a group of prime order, so therefore taking this Tate, which is somehow taking this norm of sort of all the elements in the group, is the same as taking norms from all the different subgroups. And if I had a more complicated group here, what I would want to do would not be take the quotient over by the like the Tate, but the proper Tate, where I would mod out by the norms from all the proper subgroups of G. So where you do the same thing, but you mod out by all these transfers. And this is also sometimes in group theory, just to make the connection to David's talk, this is also sometimes called the Brouwer quotient. So the group theories also have a name for this. Okay. So this was just a small warm-up. Okay. So I changed the camera. So how? So why? So question. So why does Smith theory? Why is Smith theory true? And now it's of course good that with this definition it's not a true-false statement, so therefore it's sort of a slightly weird statement. But the thing which is sort of behind much of Smith's theory is the localization theorem. So I just wanted so David did it in a slightly different way, where he didn't mention the localization theorem, but I just want to mention the localization theorem because it will also probably tie into some of the things which will happen next time, right? So, okay, so what does the localization theorem say? Going back to and this goes back to, I guess, to Quillen and Atiyah and various people, and it's very easy to prove. So it says that if V is an elementary abelian group, and X is a finite V complex A, then so then we can look at the equivariant cohomology, the Borel equivariant cohomology with respect to V. And if I don't take coefficients on the cohomology, I always mean it just with FP cohomology. Then we can look at the restriction map to V here. And now we would like to say that, it would of course be nice if these two cohomology rings were the same, which they're not. But they are the same if you invert something. So this is the localization theorem. If you localize, then they become the same. And the thing we have to invert is this SV is this multiplicative set generated by all the elements. So this has a module structure. So all of these are H star V modules. The classifying space of this elementary abelian group. And then what we have to the multiplicative set is just the non-trivial elements in H1 here, if P is equal to 2, and the Bochstein of these classes if P is odd. So let's just take this if P is equal to 2, otherwise I take the Bochstein side. So this is a product of all these. So what are all these classes? I can view them as sort of their H1 classes. So they're maps from V to some quotient V modulo Vi, where this is which is index P subgroup in here, which is isomorphic to P. So I have a bunch of, so all the classes will be sort of elements like homomorphisms from V to FP. And what I mod out by is the multiplicative set generated by all of these here. And I could even take this Euler class, E, which is just sort of the product of all of these SIs. And then what I'm doing is really I'm just inverting this one class here. And the localization theorem says that this is an isomorphism. So this gives a relation between this thing here, which is something which happens on the level of X, and also only depends on the Borel equivariant homotopy type of X. So it only depends on X up to the equivalence relation of you have maps which are equivariant maps and non-equivariant equivalences. So it doesn't depend on a stronger notion of equivalence where you actually look at fixed points. And then from this weak information, you can get information about what the cohomology is over here. And of course, what does it say here? It says here we take the Borel equivariant cohomology, but the action here is trivial. So what's written here is really S inverse V of the cohomology of BV tensor the cohomology of V. So it says that somehow we can, so from this formula, we can actually recover recover H star V, but only sort of not in a graded sense, because we're sort of having this on, which is so in the case the prime is 2, then what would be the cohomology of V here would be Fp T1 up to Tr, where R is the rank of this thing. Actually, in the statement, there's an R here, yes. So we have these generators. So then, the localizing will be the one where we localize, sort of all the elements in the first degree. So okay. Right. So the point is here that we can so for instance, we see that for instance, if so corollary of this, if the cohomology of X would be the same as the cohomology of a point, well then what it says over here, then this thing over here would just be this ring here, and then it would say that this ring, then it would say that this ring, this module here would be of rank 1 over this rank here, module here. So this implies that S inverse H star has rank 1 over S inverse V H star V. But this was equal to this thing here, so this implies that that the cohomology here would be the same as a point. Right. So this is sort of via the localization theorem. This is the basic case of the Smith theorem, which says that if you start with something which is contractible, then the fixed points will also be contractible. So this is what Smith originally proved. Yes. So this is P.A. Smith from 1970 question mark. 30 question mark. So in the 30s, right? Was that, or 40s maybe? Pretty early, yeah. Pretty early. 3 years after cohomology had been invented, you said, right? 1 year after. 1 year after, okay. Say that. The Smith theorem states that if the cohomology of X is the same as a point, then the cohomology of the fixed points will also be the same as a point, right? That's the statement of Smith's original statement. Okay, and we could do the same argument here, where we did this in a relative setting. So if for instance, if we could also do corollary here, if the cohomology of X was the same as the cohomology of an n-sphere, then by the localization theorem, that would imply that this equivariant cohomology of V of just the conon X, comma X, and we invert this class E, has rank 1 over cohomology of V with this Euler class, inverted. So this implies this, but by the localization theorem, this is the same as the thing for the fixed points here. But this says that you look worried. Vignesh looks worried. Just a sphere with some action. I'm just talking up.
I'm asking as an example, if you take sphere with the antipodal action, then there is no fixed point?
Yeah. So then yes.
I think at prime 2, the fixed points would be empty, even though.
Yeah. So minus one sphere is also a sphere. Yeah. Yes.
I'm not worried about that. Is there a particular reason you chose to write this as the cohomology of CXX and not the cohomology of special X?
No. Sometimes you have to be a little bit worried about equivariant base points. So somehow this is a safe way of writing it because there's sort of an obvious map from X to CX, which is obviously equivariant. So and it's sort of like also like maybe like disk bundle modulo sphere bundle type viewpoint. So, huh? For other groups? What? For non-abelian groups. No, this only holds for elementary abelian groups for this thing here. But then you might ask in general, like, what's the relation between the cohomology of, you can ask this. Yes. So then you can ask yourself, can you relate the K-series? So you're thinking of Siegel's formula, right? Where you're sort of taking fixed points under a cyclic group, and then you're relating that to the cohomology of the whole thing, right? You're thinking about the localization theorem in K-series. Yes.
Yeah, but I mean, there's this completion theorem, which is
right.
essentially the same thing, but you have to
The completion theorem doesn't say quite the same thing, but okay. So we agree that this has rank 1. So this implies then again that the cohomology of the fixed points here is a sphere, where you might allow for the -1 sphere, which is the empty set. So in general, as we saw in David's talk, you have these Floyd inequalities, which says that the dimensions go down. And here what's happening is that the total number of dimensions go down, but there's also some concurrence, which means that it stays the same, but it does not always stay the same. But maybe to answer Uli's theorem, there's sort of like a proto version. I mean, you can formulate some of this where you take equivariant cohomology with respect to a non-abelian group, but then you still the fixed points in the versions I know, you still have to the group will typically be abelian, but we can maybe formulate a proto theorem which says we take some cohomology theory that we like, and then we can always turn it into a Brill equivariant cohomology theory, by which I just mean, you take the Brill construction and then you take cohomology. So then you can say, okay, then we go to the equivariant cohomology here of the fixed points, and this should be an isomorphism here if we invert some class here where EA is some Euler class. Lying in the cohomology of BA. And there are versions of this form also for when you're dealing with for instance like Moraba E theory or something like that. So but of course if you do it in this way, then you might say what can you learn from this, right? So because in general, here we were sort of lucky. We almost lost no information by going to this localized ring. So we could basically get back again. If we were doing this for K theory, for instance, you could ask, okay, what would happen, right? So then you have a formula. You have a formula like this. So for K theory, and here what should A run over? A should be sort of in sort of this derived defect base, which Akil might mention next week. So for instance, for the height n theory, this would be which would be abelian p groups of rank at most n. And so for K theory, it would be cyclic groups. But then you can say this would then you would have to invert this Euler class, would be sort of be the product of all the prime ideals in the ring. And as Leonard told us, for instance, if we took the representation theory of the cyclic group, right? So then we get set of x, where x is equal to 1. But if we have to localize this in the prime ideals, in particular, we will be inverting also, so we get Q here, right? So then we get something like Q of so we'll be in a situation where somehow once we do this localization, then we can no longer make the conclusion that the fixed point themselves were contractible, because I mean there are counterexamples to this statement, but sort of since we but we do have a copy of sort of K theory tensored with the rationals inside here. So we can still get the conclusion that K theory tensored with the rationals would be trivial if what we started out with had trivial K theory. So that tells us already there that So for instance, corollary of this in cases where it's true. So for instance, K theory. So then we have that, for instance, if E1 of x is the same as 1 of a point, then this formula tells us that then that E1 of the fixed point here under some cyclic group tensored with Q is isomorphic to E1 of the fixed points here, of a point tensored with Q. So that So that statement here is so we're proving here that if x is E1 acyclic, then this implies that that the fixed points here is Q. Yeah. So in this case, you would be taking So let's see. So you would be taking CP. So you would have A mapping projecting onto CP, which would then be lying inside S1, and then you take B of this whole thing here. So this gives us some alpha, and then so this gives us so if it's a complex-oriented series, this gives us a class in degree 2, and then pulling it back would give us a bunch of classes this way here. So yeah, so we'd still have that EA would be then product over all of these alpha i's, where I would run over all of these homomorphisms. That's how I remember it. Yeah. Okay. So this was a little bit. So this E1 would be the height one. But I think this would be equivalent to showing it from a rather. So you can view this as p-adic K-series. If you want, yeah. Right. So this is one example of this blue shift phenomenon, which just says that if you the classical Smith theory would say that if a space was contractible, then the fixed points were also contractible. Then there's these higher chromatic analogs which say that somehow the same thing is true for fixed points, but we have to allow ourselves to go a little bit down in chromatic height. And why it is sort of analyzed completely by this thing, something in the coefficient here, where somehow, since we're inverting more primes, then we cannot sort of recover the whole ring back, but just some localizing of it, right? So when the
And the point is that you really don't change the homomorphic here because infinity minus 1.
exactly, that's one way to view it. Yeah. Yeah. So this is So the general statement here is this this chromatic blue shift. Which would say that if x was En cyclic, then the fixed points over A here would be a n minus k acyclic, where k was the rank of A. Yeah. So but there's this price to pay here because of this localization here. And recall, in all of these series, there will be some sort of correspondence between sort of the primes in in this thing here and BG and conjugate classes of subgroups in this defect base. So Quillen's theorem says that you parameterize the prime ideals by elementary abelian subgroups, and then there are similar theorems for I think like Siegel proved something similar for in the K-series setting. And and then there's sort of higher versions of that. due to various people. So, but this is sort of the general principle why you also get. You sort of have to analyze this ring, right? When you prove this thing, that you go down in chromatic height here. So. Okay, so this is just to say that, and this theorem here is, even in the proto version, is not hard to prove. So let me just try to prove the localization theorem for concreteness just in the non-proto version. Yes. So if we want to prove the localization theorem, then we can just observe that both sides are homology series. So both sides are equivariant cohomology series. We're taking fixed points, then we're taking equivariant cohomology, and then we're performing a localization. These are either cohomology series, and then we apply an exact functor to an equivariant cohomology series. That's still an equivariant cohomology theory. So just from general nonsense, it's enough to check this on the generators. On generators V modulo W, but what does it say in that case? Well, there's sort of two cases, right? So the one case is the case where we take V mod V, then both right and the left signs are the same. And then there's a case where we take a proper subgroup, and what does it say over there? Well, then the right hand side is 0 because we take because we're taking the fixed points. But what about the left hand side? So the left-hand side, now we're taking the equivariant cohomology of V of V modulo W here. But what is this equal to? This is equal to just the cohomology of W, and it has an H star V module via restriction. Right, that's how this isomorphism works here. But now, since we are inverting all of this product of all of these classes, these degree 1 classes, one of them will be 0 on W. So this product here will be 0 restricted to W. But then now we're inverting a class which is 0. And if we're inverting the 0 class, then the whole thing dies. So that's the proof of the localization theorem. So I thought that was nice to see, because then now you've seen the proof of the localization theorem, and I said the higher ones sort of work the same way. Questions about the proof of the localization theorem? Sorry? Sorry? This? So I'm calculated the right-hand side and got it to be 0, and then I took the left-hand side, and then I'm saying this module here, this object here has a module structure, an A star V module structure, and this structure goes via the restriction map coming from the inclusion of W into V. And I'm saying So this is a module we have over there, and then we have to invert this class. And I'm saying, oh, I'm taking this class, and then I'm just saying I said S was this, or maybe I called it E. So E was the Euler class, right, which was the product of these S, EI, I could call them, right, where I had E was projection onto EI, which was isomorph with FP. And I'm saying if one of these classes will be in the sum, so I will have a restriction which will be 0. So then my cohomology class is 0. Yeah. So I'm saying that when I multiply E, this class E by W, I get 0. Right. Pick E. Yeah. Pick EI to contain W. Right. So. Yeah. I mean so.
I think it's why is the V equivariant cohomology of the orbit same as the cohomology, but it's
Oh, sorry. Why is this formula true here? Okay, yeah. So this is. So maybe I'm confused. I mean, yeah. This is maybe what's confusing you. There's a secret B here when I do non-equivariant. Yeah. Okay. Sorry. This is confusing. This is the kind of things that you often abbreviate, but it's super confusing the first time you see it. So good thing. So when I write just cohomology of a group, I mean group cohomology. When I write equivariant cohomology of a G set, then I mean, or a G space, then I mean equivariant cohomology. Yeah, by definition, this is how we construct a Borel theory from a non-equivariant theory. We take H, and then we take the Borel construction with respect to V. And this is the same as the cohomology of a Borel construction of a point, which is the same as group cohomology of W. Yeah, sorry. Yeah. That I see that was a confusing point. And one of these things, if you made the shorthand notation a zillion times, then you cannot see the So just okay. Other questions? Huh? The right-hand side, because the fixed points. This is because we're taking fixed points of this, and there's no fixed points here, right? So because it's a non-trivial orbit, because W is now a proper subgroup of V. Yeah. Okay. Well, at least I've told you the proof of the localization theorem. Okay, and I also told you about the and I told you about these consequences, which is also good. What more can we say? We can sort of also say in this setting, you can say a little bit about what is. Okay, so now let's look a little bit more careful in the case where we have the cohomology of X is the same as the cohomology of some sphere Sn. Right, so we're again back in the situation where we're taking where we're trying to see what can we say when we have a group action on a sphere, and then you can ask yourself, well, what more information do we have about the group action just from this sort of purely homological point of view, right? And we just agreed that if we, or I don't know if we really agreed. I mean, I didn't. I sort of, we talked about that if you took the cohomology of this pair here, then this is, then this will be, this will be one-dimensional, and it will be one-dimensional in this fairly concrete way that we have this Thom isomorphism here. So the thing, so the thing to think about is that if you look at if you think about the spectral sequence for this vibration here, then it will have two lines. So, but if we took sort of the spectral sequence of the pair here, then the bottom line is sort of taken out. And this gives us an isomorphism between this cohomology of this pair and the cohomology of V. And here there's again a hidden B. And it's sort of an isomorphism on a class U, this Thom class here, in here in dimension. In this way here, it's in n+1. So that means that in some sense, what we get from a group action on something which has the homology of a sphere, then we get like this sort of one-dimensional module over H star V. And it actually comes with nice structure, which we might appreciate that this also has an action of the Steenrod algebra. So we actually both, we have this one-dimensional module, and then you might say, well, just as a one-dimensional module here, it's only given by a degree here, but we actually have a little bit more information because we have, all the Steenrod squares on this thing here. So this is nice. So then we might ask ourselves what happens here when we restrict. So we could again consider here the equivariant cohomology of this pair. And then we could take the fixed points. So then this maps to the cohomology H star V here of the fixed points. Which is again isomorphic to the cohomology of V on some new Thom class here. And we know via the localization theorem, we know that this map has to become an isomorphism when we invert the cohomology of V, or this Euler class. So this is iso. This class E. But now that does already tell us something, right? Because if this is a module here starting in some degree U, and this is another module here starting in some other degree UV, and if this map has to become non-trivial after localization, then this class better start lower down, right? Because if it doesn't start lower down, then this class will go to 0. So we know that this class U has to go to some S, some class S, X times UV, where X is some class in the cohomology of EV. Right. So this already gives us that the homology will be a sphere, but it will actually be in a lower dimensional sphere. Because otherwise this map could not localize to something non-trivial. So this is the first of one of these, like these Smith inequalities. And where can I go now? I can go here. Switch the camera. Oh man. Yes. Yes. Yeah.
Is there a way to boost formally slightly more results, still in the plan is slightly more relaxed, or do you need to come up with a different group?
No, so the point will be in the end that all of this holds for, so all of this will be things where you can do the same thing where you do, instead of doing fixed points, you do homotopy fixed points. So it depends on how you formulate. You could do it sort of formally algebraic, where you define this as some setting, or if you wanted to do it. Okay, so this is theorem of Dwyer and Wilkerson, which says that under suitable assumptions, the same thing here works with homotopy fixed points, but you need a way of sort of, knowing something about what these homotopy fixed points are in order to. And in fact, they proved something more. They proved that if you look at the okay, and they also proved, okay, maybe just let me say that it holds for homotopy fixed points, and then we also say that the other theorem that they proved which says that if you look at the cohomology, if you look at these fixed points, then you could say, well, this shows us some dimension, but only up to this localized thing. So it only shows us what happens after this localization business here. So now you might ask yourself, can you identify this ring here? You can say this ring, of course, sits inside E inverse cohomology H star V X V, which is again by the localization theorem the same thing here as X. And their theorem is that you can, okay, now I actually want to, also do equivariant cohomology inside here. So now this is cohomology of some space here, sitting inside the cohomology of something which is no longer a space because I've inverted this class. It does have an action on the Steenrod algebra because this thing here has an action of the Steenrod algebra, and then I can, because I have this element, then I just, I can extend the action of the Steenrod algebra just by using the Cartan formula. So I have an action of the Steenrod algebra on this, but this is no longer an unstable action. So if you have a class actually in a space, it has a property. If I apply a Steenrod square of dimension bigger than the degree is, then I get 0. And this need no longer be true here. Say that again? Well, this is just sort of this, like this splits as a product, right? So this is just, this is really a fancy way of writing H star V tensor over Fp with the fixed points. Yeah, so it's not something very deep about that. Yeah, so this is just because this thing here embeds into the field of fraction, or this localized thing. Yeah. Say that again? I said, so if you have a space, then the Steenrod square on x is 0 if I is bigger than the dimension of x. And I'm saying we can equip this with an action of the Steenrod algebra, but in general this rule here will not be satisfied. You have, by the Cartan formula, you know how the Steenrod algebra should act on 1 over t, and you see that this will have infinitely many Steenrod squares on it. So this cannot be, the cohomology of some space. Right. So, but their theorem is that if we take the largest unstable algebra inside here, then this actually becomes an isomorphism. So this is sort of crazy. So this says that not only can you determine, like, are these two things the same up to localization, you can somehow also like recover what the actual space is inside here. And if
There's an equal sign there before your economy.
yeah, huh? Oh, yeah. So now I have to write an on both sides if I want to, and then I have an isomorphism here.
So the result is unstable element.
The interesting result is that you take the equivariant cohomology here, then you invert this thing. It's no longer unstable. So what could be the case was, in the case where we have a sphere, right? It's we start out with this. We have this A star V of u, but then this thing here might actually. So this might actually deloop some, depending on how many Steenrod squares we have here on u. So we can basically sort of find out what the localized dimension of the new thing here will be to see how many Steenrod squares we can have on this thing here, and that will give us, the max we can pull this down, and then we pull it that many down. So we get that the new dimension of the fixed points here over Z2 here, say, will be sorry, what is the form? So the largest I where this is so how many ever we can pull it down where we still get something, where we still have, so we have to look at square I of u here, and then we ask if this is non-trivial here, and we can pull it down to the smallest I where this the largest I where this is non-trivial will be the dimension. Exactly. So the thing which happens is somehow that we look at the cohomology of this space, and then the equivariant cohomology, and then the equivariant cohomology together with the Steenrod square sort of tells us, exactly what the fixed point here will be. So right. So one of the points when Robert is speaking next week is that then you can say, well, what you can do also if you're doing this stably, if you're doing this on a stable sphere, then you can say, well, then this fixed point is no longer, sort of this class U. You can no longer sort of talk about its dimension because it might have infinitely many squares on it, but you can still sort of try to associate to this square 1 of u, square 2 of u, square 4 of u, and then this gives sort of a p-adic expansion of what the dimension should be if it had a finite dimension. So now, the fixed point spheres will no longer be actual spheres, but they will be spheres with a p-adic dimension, and the dimension you get out is simply by looking at this string of numbers and seeing here are they zero or non-zero. So this gives you, in the stable setting, a notion of these p-adic dimensions. So so what one can So why sort of the excuse for saying some of this was also because, like a long time ago, I did some work with Jeff Smith where we looked at these unstable actions on spheres, and there we used exactly sort of this trick in the unstable world where we looked at, well, what were the homotopy fixed points. So this is with me and J.H. Smith, Jeffrey Henderson Smith, which is not related to the other Smiths, where the first thing we observed was that if you have a p-completed sphere and take the homotopy fixed points, then you get a new sphere out of lower dimension. So this becomes now a new sphere here of some dimension d of p for some d of p, and I gave you the argument why this in the unstable world, so this in the unstable world this will be an actual number, and it will be less than p, less than n. And these numbers here, just basically by this argument I started to show you here, satisfy what's called the Burrell-Smith inequalities. So these numbers, so you can look at these numbers for all the different spheres, and they satisfy these Burrell-Smith conditions. And this will just be, okay, now I'm here. So this gives you sort of information about what these fixed points can look like. And the argument is just using this homological, this localization theorem. So this is a way of classifying the action, right? Sorry. So I start with, so this is a sphere. So what I mean by this is that I have a homotopy action on the sphere. So what I give myself is then a map from BP into B odd of the incompleted sphere, right? So I have a Borel type action on the end sphere. Oh, there's a prime P, and then this is for. The dimension of the new sphere. Okay, so this should be this would be a new sphere, and I just gave you the argument why this new sphere has to be of lower dimension. No. This is what classifies the action. The action, even this homotopy sense, is classified. It turns out by all of these numbers. So the action is, Well, so you have this number for all the different subgroups. So yeah, sorry. So it's always what happens when you're trying to go quickly at the end. Then you say skip a step, and then you have to explain, and then it takes longer time. So then, what I mean is that you have a thing which to each subgroup Q of P associates this number Q, which is sort of the dimension of the fixed points under Q, right? So then you take the homotopy fixed point under Q. That will again be homotopy equivalent to some Q sphere of a lower dimension, and furthermore, there will be relations between these numbers, which will be sort of combinatorial relations, sort of basically saying that it's determined by. There's a lot less information than just all the numbers, and the statement is then that classifies the action. So, and this, yes, we are out of time. So, so this says that the map then from P, so they're all linear basically. Of the end sphere. This is subjective here, and the isomorphism here is, and if I put a P completion here, then this means that rho is equivalent. So they're all linear, and they're equivalent here if and only if the irreducible components are pairwise Galois conjugate. This classifies these actions on these for P groups. And we can also do something for. It's a long story there, but Robert will tell you something about the stable case next week. So now you're warned. Okay. Yes?
There's an action of cohomology on homology, and so you could phrase in principle the localization theorem for homology.
Yes.
Is this true?
You could phrase the localization theorem for homology.
You invert like in the sense of modules instead of springs.
Yeah. But then the map goes the other way, no? But also you have a co-module structure of the coefficients, right?
But I was thinking of the action of the cohomology on the homology. There's an action of cohomology on homology, and so you can invert cohomology
Okay.
So actually, you take orbit to a point, you're going to get something that looks like Laurent series mod power series, and so t is going to continue down, and so for t, you just get a 0 for everything.
So you get 0. Okay, the answer is no. Okay, other questions? Say that again. There was a finiteness assumption on X. Yeah, so so that was used because I did this thing where I just had to check this on orbits, and if I wanted to prove something for infinite things, I would need to take some sort of limit, and then this argument would not work. So this is so in that argument I was using that I only attached finitely many cells. Then for this more general story, which I sort of hinted at, where you sort of replace fixed points by homotopy fixed points, then what you have to, that you only have to make a homological finiteness assumption, right? So this is just, in the homotopy sense, actions on these, on spheres, right? So I'm not assuming necessarily that I can model this by any finite complex a priori. So it turns out actually in this case that you can, but this will not be the case for general finite groups, but it happens to be the case for P groups. But but the starting point is that we do not know anything about whether we can model these by finite complexes or not. They're just sort of arbitrary things which has a finiteness assumption in homology. And I'm identifying two things which, if they can be connected by a zigzag, are maps which are equivariant maps and non-equivariant equivalences. So the Brill equivariant sort of story, yeah. The finiteness in homology is enough, yeah, for this, yeah. So this is the whole niceness about doing like things with homotopy fixed points and things like that. You only have to have these weaker finiteness assumption. And it's the same thing you would also do in algebra. So then we came up in David's talk, right? Then you somehow, for these Brill conjecture and things like that, you're looking at, it's sort of the weak, you're doing equivariant homotopy theory, but in this Brill equivariant sense of homotopy theory, you're not actually like requiring some information about the actual fixed points, which, gives it a different flavor, but actually turns out sort of in some sense closer to what people classically have studied in algebra. So. Say that again?
So you said that like a global equivariant,
Yeah.
there's like this class of subgroups I need to look at.
Yeah.
Is there like a novel story if I have like a genuine equivariant?
Yeah, you always have induction theorem for some like defect base. Yeah.
Is this defect base, for example, for K theory, it's a supergroups and so on, related to what Leonard talked about, that we can induce K theory out from?
Exactly. Yeah, this is the same. Yeah. No, exactly. I know that's why I was trying to sort of at least sort of mention all the different lectures. So, but it is the same. And I think it will also be something in next week. And yeah.